So good afternoon all. I welcome all the course participants, course coordinators attending this program from their respective universities. So today's lecture will be taken by myself and Shri Ashish Joshi ji, and lecture will consist of the GNSS signal structures and the various data formats. I hope today good number of people have experienced the earthquake, and you can relate that the topic which we are covering in this particular module and the GNSS course is of quite relevance to this kind of an event, because our continuously operating reference stations give lot of information, as we have discussed in the previous 3 lectures and 1 demonstration. So overall what we see that satellites are being used for large number of applications, including the weather forecasting, communication purpose, TV broadcasting, satellite telephony, and so on. This is what I am trying to tell you, besides the activities which we are regularly involved in the remote sensing, such as the acquisition of the images through the various satellites for various purpose, and in which we require the GPS data for the purpose of the georeferencing or the satellite triangulation of the data sets. Now here the signals are very important because they are traveling from the satellite to the ground receivers, and being electromagnetic radiation in nature, finally they may have interference kind of problems with various type of communications. Like there are DTH services are there, this radio systems are working, we have FM radios also, interactive entertainment and games. Wherever some kind of EMRs are involved, UHF VHF antennas are there, so they may have some intervention. So because of that, the International Telecommunication Union ITU, through the World Radio conferences, try to manage these various signals and their respective bandwidths, so that the important applications, and particularly those applications which are international in nature, like the flying of aircrafts uh, from one country to another country, those services are not getting affected by the interference between various signals. So this we have already discussed. Some of that I will revise for the purpose of the signal. We have discussed that in the basic structure we have two L1 and L2 carrier waves, over which the CA code and P code are modulated, and besides that we are getting a satellite message consisting of the almanac and the ephemeris data being received at 50 bit per second. That was the basic structure of the GPS signals earlier. However, with the increased requirements, particularly for the indoor applications, L5 has been added, which was having the anti-jamming features also. And for improved civilian applications, L1C, L1, L2C, these codes are also added in the due course. L1 is 19 centimeter wavelength, L2 is 23 to 24 centimeter wavelength, L5 is 25.5 centimeter wavelength. And these are having the bandwidths of 24 megahertz, 22 megahertz, and 28 megahertz, respectively, for the L1, L2, and L5 carrier waves. Then the IM code is for the defense purpose, that also. So this is the current structure of the GPS. Now the GPS fundamental frequency is 10.23 megahertz, whereas for the GLONASS it is 5 megahertz. So similar description will be there for different satellite systems. So now if this shows a summary how various bands are distributed along the electromagnetic radiation as per their wavelength or the frequency. So GPS bands are shown here, various L5 band, L2 band, L1 band. Then GLONASS bands are shown here, G3, G2, and G1. Then Galileo bands, E5A, E5B, E6, E1, and the Galileo search and rescue downlink, that is also shown here. Now these bands are also used for other purposes. Like for the aviation radio navigation signal, this entire range is used as shown here, as well as this one. So L1, L5, these ranges are also used for the aviation radio navigation services. Then the radio navigation satellite systems also use various bandwidths here. So we have to see that there are no interferences which are happening in the particularly frequencies, so that particular application is not affected in a worse way. Thereafter, we have seen the different kind of services and the frequency bands for the GPS, GLONASS, Galileo and the BEDO. Galileo had recently defined a high accuracy service also, HAS, which is a high accuracy service, and they have a commercial plan, so they use a lot of services for particular agencies, you can say, for police and anti-fraud agencies, for search and rescue purpose, for commercial service, safety of life service, or the open service. Similarly, we have standard precision service and high precision service for the GLONASS, standard positioning service and precise positioning service for the GPS, and open service and authorized services for the BEDO. So like that, different signals distributed over different frequency bands, they are being utilized for the GNSS based applications. Some of them, as shown here, we can see that some of the wavelengths, they are same, common for the various signals. So this helps us achieve the interoperability also, which is required in a GNSS, and largely provide a good solution by improving the redundancy in the computation. A large redundancy give rise to a better error distribution function, and thereby achieving a higher accuracy. Now the different codes or the methods which are used to identify each signal, they include the FDMA, in which specific frequencies are allotted to transmitter in order for their identification. And in the case of CDMA, the code distribution multiple access system is used, whereas in the TDMA, time division multiple access system is used. So particularly in case of the GLONASS, earlier, before 2006 era, it was using the FDMA signals. Now since the GNSS concept came and the single receiver has both the GPS and GLONASS, so GLONASS also provides signals in the CDMA also. Now these signals provide the location of the satellite or some information on how to determine it through the various parameters available in the signal. Details of the satellite clock status are also provided. The time computation is also done, as I have told you, that T1 is the time at which the signal starts from the receiver. T1 is the time when the signal starts from the satellite and it reaches the receiver at time T2. So T2 minus T1, that provides the delta T component, which is the time of travel between the satellite and the receiver, and that is utilized for generating the spheres using the pseudo ranges for the computation of the location of the receiver. Now here we also have to note that initial solution were based on the codes only, CA code and P code. We have seen that the CA code and P code have different complexities, whereas over the time the computation of receiver is being done with the help of the carrier waves also, using the phase based solution, because phase based solutions emerge as more accurate solutions than the code based solutions. So code based solutions are able to provide meter level of accuracy after the differential GNSS solution, whereas the phase based solutions, they are able to provide centimeter to millimeter level of accuracy and the precision. So CA code is using a gold code with the 1023 bit long code, whereas the GLONASS is using 511 bit. Chipping rate is 1.023 megahertz for the course acquisition code. Now similarly, this we have discussed in the previous lecture also. We can see that the P code is much more complex as compared to that, and it's a quite long code, requires 266 days to complete. So CA code frequency is 1 millisecond. So by the time I speak, thousands of cycles for the CA code are already over. Now the military receivers basically get hold of the CA code first, because picking up the P code is a quite complex job. So based on the C code, they are able to synchronize and get hold of the P code also. Now L2C, L5 and L1C, these are the new signals which has been added from block 2RM onwards. So 2RM onwards we have L2C, block 2F onwards L5, and block 3 is using L1C. So this is to provide more secure system along with providing more accurate signals for the civilian applications with the help of the L2C and the L1C, and with the help of M code for the purpose of defense also. So primarily these two pronged application has been made here, one for the civilian and for the military purpose, that the codes are increased which are helping the achievement of the higher accuracies. So in the L2C code we have civil moderate code which has a 20 millisecond time period, whereas the civil long length code is also there which has a 1500 millisecond time period. Similarly, L5 has I5 code signal and the Q5 code signals at 10,230 bit long at a frequency of 10.23 megahertz, which is the fundamental frequency. Now the block 3 is designed for more cyber security purpose, as I have told that it requires the changeover of all the hardware systems on the ground. So ground segment is under total replacement, and it is using a CNAV code which is 1800 bit long, and it is more flexible than the legacy navigation code, that is L1 code, a CA code on the L1 frequency. Then the navigation system also require the navigation message in case of the GNSS services. The ITU defines that which agency is going to get which frequencies. Like in case of IRNSS, they have allotted us L5 and S band for the use of the IRNSS receivers. Now they have allowed the use of L1 also. So there is a management which takes care of the different bandwidths for different GNSS systems, and based on these the different signals and codes are there which help us in identification of the satellites using the pseudo-random codes, the transmission of the pseudo-Keplerian orbital elements, clock correction parameters, and the ionospheric and tropospheric correction parameters also. Now these things are very transparently shared nowadays, so lot of information we get with the broadcast ephemeris data itself, wherein we get a solution then and there itself in a standard alone mode also, whereas in case of the availability of a modem or satellite based correction parameters or internet based correction parameters, we can have the differential solutions also in real time. So this distribution of different blocks was also covered in the previous lectures, that about 12.5 minutes will be required to download the data of 25 satellites. Almanac also we have discussed in the previous class. This class particularly I want to show you online that how we can go on these different pages. So for that I will take you to the internet for some time, so that what we have been discussing on the slides in the previous lecture you get acquainted with the website also. So here we have the IGS station website, where we can do the search for various signals, various IGS stations across the globe. So here we can search also. So we can see that in India now a lot of stations are there. So this by this name we are getting from the IIT Kharagpur actually. So they have put a Trimble system. Okay. So now here we can zoom on to the Indian region, and now we can see that in the Indian region we have different places, like IIC Bangalore is there, and you can just click on that, so you will be able to get the information about the particular center. Let me show you 1 minute, it is taking time. Yeah, so this is our uh, National Remote Sensing Center RC West location at Jodhpur. So you can get the latitude longitude of the place and the elevation data, country and region, last data available date, and you can see the 10th October 2023. So the 3rd October data is being compiled, and station info can also be seen here on the web. Okay. So the network can be viewed, and station overview. Okay, it is taking some time for the net. Similarly, data and products can also be seen on the IGS website, which can be downloaded for the processing with the precise ephemeris data. So these data sets are available for realization of the ITRF, monitoring deformation of the solid earth, monitoring earth rotation, monitoring variables in the hydrosphere. So we can see that these various headings what we see here, they themselves are uh, big science questions actually, and different agencies take care of them, the ionospheric and tropospheric monitoring also. So with related to these things, various formats of datasets are available. So GNSS precise orbit data in the SP3 format and the SP3 format, they can be downloaded from here. For the earth rotation parameter, we can download some of the files from here respective. These files are specifically required if we are doing the processing in some of the scientific softwares like the Gamut or the Bernice. In that case, we need to go to these sites, and for specific periods we have to download the different data sets. So all this information is required. Now the Indigo is also a operational way where the NASA is trying to use different type of services which we discussed in the first lecture, including the VLBI satellite laser ranging stations, DORIS, all combined together for the purpose of the space geodesy. So similarly, almanac charts can also be seen live here, date wise and they can be downloaded also. So this is one for the GPS almanac, which is available today only. I have taken a screenshot to place it here, and this is for the GPS. And the different agencies, they are collaborating together also, so that you can see that here from the Russian website basically we have the access to the GLONASS, Almanac, BEDO, GPS, Galileo. All the four are available on the same website. This is the old screenshot. Now the interface has changed. Just now the new interface I have shown you for the International GNSS station. So this is one for the overview of the IIT Kanpur station, and then one is for the ISC Bangalore. So you have the photographs also for the station, and the Jodhpur station also. So these different stations can be seen from the IGS website here, and the data sets can be downloaded. The entire list can also be downloaded from the in an Excel sheet from the 516 stations. So these are the current stations which are totally operational as of now. Now GLONASS is using the antipodal design, wherein the opposite satellites over the Earth. So if we are considering about 24 satellites, so there will be 12 sequences of L1 and L2 as per the discussed formula in the previous lecture, depending on the 1602 megahertz plus n times the 0.5625 megahertz. So 12 set of frequencies will be used for the 24 satellites. So here in case of the GLONASS, L1, L2 are not fixed single values, but they are different for the 12 sets. So for the antipodal satellites towards the two opposite sides of the Earth, we will have same codes being transmitted at same frequencies. However, they cannot be received by the single receiver, because the GNSS receiver cannot receive both the signals from opposite sides. However, the same code at different frequencies will be achieved through the satellites which are available in the single coverage area. Maybe I will just repeat it for your convenience. So when we are placing a GPS or the GNSS receiver at the same place where we can receive the GLONASS, so from that particular receiver we can receive the same code on different wavelengths, because the wavelengths used are different as shown by this formula for L1 and L2. However, the satellite which is on the opposite side, that cannot be received. So if a receiver is on this part of the Earth, it can receive the signal from satellites which are towards this part, and a receiver placed here can receive the signals from this part. Okay, and the frequencies are used differently for the different satellites. Now coming to the Galileo, we have seen the different distribution of the wavelengths in the E5A, E5B, and the E6, L1 and E5 as provided here. Now this system is also a 3 orbit based system. In Europe also, as I was telling, that improved values are possible through the Eurofix service, wherein they are using the satellite based corrections to be transmitted through the SysNet protocol. So they are providing a differential corrections and phase measurements in addition to the messages of the real-time kinematic implementation. Then for the IRNSS, we have currently 7 satellites in operational in orbit, and the final version with 4 spares will also be soon utilized, and this will be explained in detail in the lecture on the IRNSS separately. So here L5 and S-band were used for the transmission of the signals. Now from the NVS01, the third satellite third frequency which has been added to the latest satellite which has been launched recently, we will have all the three wavelengths L1, L5 and S. So that will help us in the interoperability also for the IRNSS, and we are in process of increasing the footprint of IRNSS also from 1500 kilometers beyond the Indian borders to 3000 kilometers beyond the Indian borders. So that will benefit the entire SARC region for the IRNSS. So this is the distribution again shown for the IRNSS bands along with the Galileo and the GPS bands, as we have discussed for the GPS along with the GLONASS and Galileo in the previous slide. So here we can see that E5A and E5B are there from the Galileo. So quasi-Zenith satellite system also, it is initially planned for the 3 satellite combination to provide the regional navigation system for the Japan. However, it is also aiming at 7 satellite based system in the very near future, by this year or by next year. As per plan, it was to achieve 7 satellites in 2023. So that will also be done, and these are also providing the facilities. Some are on the chargeable basis also, and this has lacks interoperable service with the Galileo also. Japan is also again using a Japanese Geodetic system which uses GRS 1980. The offset between the JGS and the WGS84 is less than 0.02 meter. See, when we are talking about different systems, GPS, GLONASS, Galileo, BEDO, we have seen in the previous lecture, all are using different Earth-centric, Earth-fixed coordinate system. However, the transformation parameters are well known and well computed. Then BEDO also we have discussed that it is having a 7 orbit based design, and the development was from BEDO 1 to BEDO 2 to BEDO 3. It is also using different signals for the purpose of open service and the authorized services, using the inclined geosynchronous orbit, geostationary orbit and the medium earth orbit satellites. Now different position formats are used for the degree minute second, degree minute decimal or degree decimal systems. All these are possible in the handheld GPS as well as in the differential GPS systems. Now here I would like to quote here the John P. Snyder, that every map user and maker should have a basic understanding of projections, no matter how much computers seem to have automated the process, because we have about 400 plus projections which are available now in the softwares. So we need to have some understanding in order to select final one for the specific application. So here I have shown you the UTM zones. So we have to understand the UTM zone system also if we are choosing UTM as the projection for our work. So here different I am just showing an example which we have done for the Rudrapur site, wherein the control points has been taken. So the GNSS, our Trimble R7 has been used with the .dat format. So this is the base station which was there, and these are the rover station points for which the baseline processing has been done. So here we need the RINEX converter also, and we have different formats as we can see here, .dat, .tgd, .t00. So we have to bring in case we are using multiple vendor GNSS receivers, then we have to bring all to a common format for a particular solution. So there we may use the RINEX converter. So RINEX is the random independent exchange format for the exchange of GNSS observation data, broadcast information, and the meteorological datasets. Whereas the SP3 is used for exchange of precise orbit and satellite clock information. The International Earth Rotation Service and International GNSS Service also use different formats for providing the data, as I was showing you in the website in the data and products. So from here we can get the different formats and the data sets for the troposphere, ionosphere, earth rotation parameters, which we can download and which we can use in the processing. If we want to process in some commercial software, then these may not be uh, required. Commercial software like a GeoOffice or Trimble Business Center, we may go up with the standard models. But if we want to utilize this, then we can use the Gamut or the Bernice software. As per the requirement, we can use the tropospheric SINEX file for the antenna exchange format, for the ionospheric format, and for the clock RINEX format. So these different formats are there. Currently, RINEX 4 is being utilized. So that also we have to see, because different stations which are working across the globe, they are using different formats. So that is another challenge when we are working with the uh, more number of stations, because we will need the conversion from one to another. So this is the CDDIS website from where we can download different data sets for the particular application. So here we have shown for the L1 L2 for the ionospheric free linear combination. This is for the GPS. Here it is for the IRNSS satellite antenna corrections, which are also visible now in the RINEX format. So RINEX data has already defined spaces for the IRNSS parameters also. This was the Indigo service which I was explaining for the purpose of crustal dynamics, using all the feasible techniques, satellite based like ILRS, VLBI, DORIS and services. So these are the different portals which are of high usage when we are going for some detailed studies, and this shows different type of external data files, survey metadata and command files. If we are aiming for some highly accurate solution, so the earth orientation parameters file will have ut1.pol. Notation tables can be downloaded. Lunar solar ephemerides are also available. GPS time and UTC time that we have discussed, the international atomic time, those differences are also available. Receiver antenna code. So these different format files, many of these are not required when we are going with the standard solutions. But if we are going for some crustal deformation kind of studies, that time these files will require to be downloaded for a specific period of survey and utilized. So ocean loading files are also there for the various parameters. Clock code biases are also there. So these files will be required and can be utilized for the processing. So the GNSS data consists of the receiver observation data, the broadcast orbit information of the tracked satellites, and supporting data such as meteorological data. So in nutshell, basically what I want to specify here is that we have seen that a hand alone device which we are using in a standalone mode can provide us an accuracy of 10 to 20 meters, whereas when we are doing the GPS survey with some standard softwares without using much of the files which we have shown here, there we can achieve an accuracy of 10 to 20 centimeter basically. But if we are using these files, then we can go for some higher accuracy, wherein centimeter or millimeter level of observations can be done for the purpose of the crystal deformation. So now I will stop here, and we will have a break of 2 to 3 minutes, and then we will continue with Shri Ashish ji.
Good afternoon all. Myself Ashish Joshi. In next part of this lecture, I will tell you about the RINEX data format of the GPS receiver and the precision ephemeris. So, what is the RINEX data format? So, it is a kind of GPS receiver data format. So, the full form of this one is Receiver Independent Exchange Format. It is developed by the Astronomical Institute, University of Bern in 1989. So initially, what was the problem? Actually, all the manufacturer of the GPS receiver have their proprietary file format specific to their receivers and processing software. So the problem is that the GPS raw file is have some that proprietary file format, and if we want to process the data with another software, or we have to use the multiple GPS receiver data files, so how to actually decode that data files? So the problem is solved by defining one common data format. So that is called the RINEX format. So it is the independent of the particular GPS receiver. So the name is like that, RINEX, that is the receiver independent exchange format. So it is independent of the any proprietary file format of a particular GPS receiver. So in the first version, it actually was released on 1989. After that, several versions of RINEX was there, version 2 in 1990, and the version 3 is in 2007. Actually, version 3 have the significant changes in the RINEX format. After that, currently there is a RINEX 4 format. So this RINEX 3 and 4 have similar type of format with some extra things in the RINEX 4. In the RINEX 2 versions have actually 4 ASCII files type. So we have the observation data file, we have the navigation message file, meteorological data file, and GLONASS navigation message file. In the RINEX version 2.10, we have the more files, like 6 ASCII files are there. Apart from the 4 files, we have the geo navigation message file and satellite and receiver clock date file. Okay, so in this 2.0 and 2.10 and 2.11, we have several files. So we have the multiple observations was there. So this thing is actually overcome by the RINEX 3.0 format, in which there are basically 3 types of data format and data files, which is the observation data file, and the navigation message file, and the meteorological data file. So in the observation data file, mainly we will deal with the GPS measurement, which is the pseudo range. So because we know in the GPS we mainly calculate the range, so that range or pseudo range is calculated through the observation data file. Okay, after that, in the GPS navigation message file, it will consist the ephemeris or orbit information, means where the satellite is located. Means we have to know about the XYZ velocity and time. So where the position of the satellite, it is known through the GPS navigation message file. And third file is the meteorological data file, which have the pressure, temperature, relative humidity, and another atmospheric parameters. So basically this lecture will concentrate more on the observation and GPS navigation file, which deals with the positional things, and we are not going to the details of the meteorological data file. So in the observation file in the RINEX data format, we have the 3 main things. One is the time, one is the pseudo range and one is the phase. So the time actually in the RINEX format, it is given in the GPS time and it is not as a universal time. So normally in our satellites images and doing any remote sensing application, we use the UTC time, universal time. But in our GPS we have the GPS time. Okay, so there is some time lag and some difference in GPS time and universal time, and the conversion we have known. And second thing is the pseudo range. So it is the distance from the receiver antenna to the satellite antenna, including the receiver and the satellite clock offsets. So normally the range is the distance, and due to the offsets and the bias in the receiver GPS, we are calling that range as a pseudo range due to the difference in the timing of the receiver and the transmitting GPS antenna. Okay, and third is the phase is the carrier phase measure in the whole cycle. So this phase information is also actually in the RINEX data format. Through phase also we have a number of observation and parameters we can derive. So how is the file name of the RINEX data format? So file name is actually, if we can say, we have the file in say date is around 18 September 2020. Okay, so in this date we will start with the file name with the day of the year. So first is the day of the year we have to calculate, and what is the station name. So say our station name is, say it is generated at IIRS. So IIRS is the station name, first four character, and then there will be a day of the year. So first four character will be the station name, and then there will be the day of the year. So what is the day of the year? So we will have to calculate for a particular day what is the day of the year. And after that there is the two digit there is a file sequence, means it is a daily file or it is an hour file. Okay, means it is the file is obtained in one file per day, or we have in the basis of the hour. So if it is a daily file, then we have to put 0, otherwise we have to place like A, B and X. Okay, so say if we have the daily file and the day of year is around 18 September 2020, then the day of the year is coming 262. So our file name will become IIRS 262. Then it is a daily file, then we have the 0, and after that we have the year, 2-digit year number. So we have the year is the 2020, so that is the 20, and in the last we have what type of data file. So we have the observation file or navigation file or meteorological data file. So as per the data format version, we have the if we have the RINEX format, we have the three files like observation file, GPS file and the meteorological data file. So we can put like observation file IIRS 2620.20O and the navigation message file as IRS 2620.20N. So this is the how from the RINEX format file itself we can know from where it is generated through the first four character, at which what time it is generated, and what is the actually it is acquired daily or it is a hourly file, or what type of the file and which year it has generated. Okay, so from the file itself we can know certain things about the file in the RINEX format. Now we have three files in the RINEX format. First is the observation file, second is the navigation file, third is the meteorological file. So first we will look into the observation file. So what are the observation file? So in the observation file we have the basic parameter we are actually interested is the pseudo range, and actually pseudo range is calculated through different frequencies. So we have, or we can measure through the phase measurements. So we have different codes at which frequency we are measuring the pseudo range. So like L1 and L2 are the codes like phase measurement. If anything is like L1 and L2, that is the phase measurement, and C1 code is there, that is means like pseudo range calculated using the CA code on L1 frequency we are finding for the pseudo range. Now P1 P2 is the pseudo range using the P code on L1 and L2. Okay, so these are some of the codes at different versions of the RINEX, like L1 L2 C1 P1 P2 D1 D2 is the Doppler frequency. Okay, likewise in 2.10 we have the different codes are there. So actually the versions have different satellites, GPS satellite sensors, like somewhat have the GPS and GLONASS and that one. So accordingly we have different codes, and the different codes are increasing in each version. Now in the RINEX version itself, for a particular different GPS constellation wise, we have the different codes. Like for the GPS we have the L1 and L2 and L5 frequency band, and we have different frequency and different codes, like C1 P1 is there, C2 P2 is there, and CS. Accordingly GLONASS is there, Galileo is there, and ISRO is there. So for a particular GPS satellite constellation or GNSS satellite constellation, we have different codes in the observation file. In this we have different codes for the GPS itself. So now we can see the how the data look like in the observation file. So in an observation file we can see we have the first is the header section. So this is the observation file in the ASCII format, and this is the data section. So we have the two part, one is the header section and one is the data section. So header section have the codes in it, actually what type of information is containing in the data file. So there are certain numbers are there, some information is there, but what is that number? So that numbers is actually tells by the header file. So we have the codes like L1, L2, P1, P2, C1 and S1 and S2. So what are that codes? So that codes are defined like L1 and L2 is the phase measurement on L1 and L2. C1 is the pseudo range using the CA code on L1. P1 and P2 is the pseudo range using the P code on L1 L2. So here there is the L1 and L2. So their first observation is the phase information, and after that P1 and P2 is the pseudo range information. Okay, so we have the different data numbers or data information is there in the data section. So we have the time is there, pseudo range is there, signal strength is there. So signal strength is the S1 and S2. So how, if we are calculating any pseudo range, how much is the signal strength is that there at that time. So all that observation codes are available in the header file, and corresponding what is the data, it is actually available in the data section. Okay, so this is the observation file in the RINEX format. So in this data section itself, so first we will see that there is a time information, and there is the number of satellites. So how many number of satellites are there, and what is the satellite number. So if any particular satellite, so if the observation of particular satellite, so what is the satellite number is there, so that is the unique satellite number is given. And after that the observation data. So this is the first data, after the second data, third data. So with the time of acquisition we have the different data and different ranges are there. Okay, so this is the observation file, from where we are more interested to calculate the pseudo range. Now second is the navigation file. So basically the navigation file will give about the 6 Capillarian elements, means it will give the satellite parameters. So we know the satellite orbit is we can generate the satellite orbit using the 6 Capillarian elements, which is given by the semi major axis, eccentricity, argument of perigee, inclination, ran is the right ascension of ascending node, and true anomaly. So these 6 Capillarian elements, if we know this, then we can able to generate the orbit. So if this is a satellite orbit in the blue color, so this blue color represent the satellite orbit, and this is the Earth equatorial plane. So this x-axis is the direction to a particular fixed star, and how much it actually the this is the ascend where the satellite orbit is intersecting with the earth equatorial plane, so that is called the ascending node. So this how much angle it is making with respect to the x-axis, that is called the right ascension of ascending node. And how much is the angle it is making with the perigee point. Perigee is the nearest point of the orbit with respect to the earth, that is called the perigee. That is, this angle is called the argument of perigee. And this is the equatorial plane, and how much angle it is making with respect to the equatorial plane, it is called the inclination. And this is r is called, this is called the this is called the position vector, and nu is called the true anomaly. Okay, so this is the angle which is it is making with respect to the perigee. So true anomaly actually tells the position of the satellite. So as the satellite is moving, this angle will change, and this true anomaly will tell you about what is the position of the satellite. So these different parameters will tell you about the position of the satellite also. So we can generate the orbit from the satellite position. So the size and shape of the satellite is actually we can determine through the semi major and eccentricity. Orientation we can actually calculate through the argument of perigee. And inclination and RAN will give the orbital plane, how the orbital plane is inclined towards to the equatorial plane. And third is the true last is the true anomaly, which is telling the satellite position in the satellite orbit. So here we can say the true anomaly is responsible to tell the what is the xyz position of the satellite. Okay, so all this parameter actually is given by the navigation file. Okay, so all these 6 capillarian element will actually consist in the navigation file. So from in these 6 parameter we can generate the 16 parameters also. All these parameters are the derived parameters from that 6 capillarian element parameters, like we have the mean anomaly, mean motion difference, and we have the rate of right ascension, rate of inclination, and some correction we are giving to the argument at latitude or orbital radius. So these are some of the parameters which can derive through the capillarian elements. So we can have the 16 parameters for a particular satellite to define the orbit. Okay, so how this parameter actually comes in the navigation file of the RINEX format. So similarly in the observation file there is a header section and data section. Similarly in the navigation file there is a header section and the data section. So this is the normal in the matrix form it is shown how the data is arranged in the navigation file. So we have the different parameters, like this is the square root of the semi major axis, eccentricity is there, RAN is there, argument of perigee is there, inclination is there, and mean motion is there. So different parameters are there which we are interested and which we can extract and we can use for the knowing the position of the satellite. So in this navigation file we can see here it is given as a time. This parameter represent the eccentricity, this represent the inclination, and this is the mean motion difference, this is the mean anomaly. So this true anomaly and mean anomaly, it is actually we can just relate and we can find out the position of the satellite. And here it is the square root of the major axis, and RAN is this number. So from this navigation file we can derive the many parameters of the satellite orbit, and through that we can have this position of satellite, like this is the standard range equation, means this is the range, this is the square root of x minus x set, y minus y set, z minus z set. So x set, y set, and z set are the positions of the satellite. So these positions actually we can derive through the navigation file, and this range or pseudo range we can derive through the observation file. So if we have the 4 satellites, then we can have the 4 equations, and we can derive the actual point value like x, y, z values. Okay, so this is the this x set, y set, and z set is derived through the navigation file, and this observation file actually is derived, this r is derived through the observation file, and with the help of these parameters we can actually calculate or estimate this x, y, z of the unknown point. So this is the overall methodology how we can extract the position of any point on the earth surface through the GPS satellite. Means we have some observation file, navigation file, we have to extract the parameters, and using that parameter we have to establish some of the non-linear equation, and we have to solve that non-linear equation to derive the xyz point. So this is the visualization of the positions of different satellite, like 7 satellites are there. So for a particular GPS receiver at the Bangalore, so from there we have one RINEX file is there. So we have decoded in the MATLAB, and in the MATLAB we have plotted the position of the satellites at a particular time at a GPS receiver, and we have at particular time we have the position of different satellites at of that constellation, and we can plot that on the earth on the earth or the in the geographical map of the earth. So this is about the RINEX format. Now second thing is the precision ephemeris. So that actually it deals with the how precisely we are calculating the xyz of the satellite positions. Okay, means we are having some xyz values. So but this xyz values are in a real time it is not so precise. So that precise value actually is given by different networks. It is called the International GPS Service for Geodynamics. So IGS is the voluntary federation established in 1992 for give the precision ephemeris. Means we have the satellite positions at a particular time, but how precisely we are actually finding this xyz, because xyz is actually we are calculating it, we can may have some errors. So that errors actually is minimized if with the multiple observation and at multiple positions of the GPS receiver station. So in the precision ephemeris what it will do, it will give the precise xyz positions of the satellites for your GPS, so that we can calculate our GPS point at a particular time more precisely. Okay, so this is actually this is have different products like GPS satellite ephemeris. It will give GLONASS satellite ephemeris, earth rotation parameter, IGS tracking station coordinates and velocities. So different products it will give, and with the help of that we can have the precise satellite orbits. So they will give the orbits at different levels of products. We have the broadcast we have the ultra rapid products, we have the rapid products, and the final products. So as the latency is increasing, so we have the precision is increasing. So initially in the broadcast we have around 160 centimeter level of accuracy, and in the final products after some days of 13 days we can have the orbits of the 5 centimeter accuracies. Okay, so we have different products like final product which can be available at 12 days latency, and the rapid product it is around 17 hours, and the ultra rapid product it can be released hourly. Okay, so these have the different products. So it depends on our application at which product we want to use. Means initially we can use the ultra rapid product for a particular precision, and as we are getting the more precise orbit, we can also improve the positional accuracy of particular point by using the precise ephemeris orbits. So what we have to do, we have to replace that xyz coordinates or in our GPS with this precise orbit. So initially in the navigation also we are having some xyz values, but that values are not so accurate. So to increase the accuracy we will replace that navigation file parameter with the precise ephemeris files, so that the geolocation or the positional accuracy of particular point will be higher. So in the precision ephemeris, actually it is given as a SP3 format. It is called the standard product 3 format. So here also we have the different data. So here is the header file, and there is the data file. So we have the first is the x, y, z in the kilometer, and this is the state vectors. So different state vectors are there. So we have the time interval of 15 minutes. So every 15 minutes we have the observations, and there also for a particular this time we have this type of different state vectors are there for a particular satellite. And after 15 minutes again this set of information we will come for x, y, z, and what is the clock error and standard deviations. And all this information actually is given in the ECF coordinate system, which is the centered earth fixed system. So basically normally in the coordinate system we have the ECI and ECF coordinate system. So in the GPS the XYZ is given as a ECF coordinate system to calculate the position of any point. So this is the using the precision ephemeris we have plotted the one satellite orbit vector from the precise ephemeris sp3 file. So again in the MATLAB we have plotted how the satellite track is observed. So that XYZ positions we have plotted in the on the earth using the information obtaining from the sp3 file. So what we have done, we have extracted the XYZ at a particular time. So we have different time stamping is there, and for a particular one satellite, this satellite different position vectors are there, and that we have plotted. Okay, once it is available in the 15 minutes, we can also interpolate at a particular time also. So we should have a good interpolation techniques to interpolate the satellite orbit vector also. So that's all from my side. So in this lecture we have studied basically about the RINEX format and the sp3 format. Okay, so RINEX format is mainly deal with the GPS receiver, in which we have different files: observation and navigation and a meteorological file. Observation file is given and will give the pseudo range. Navigation file is given will give the XYZ of any particular point, satellite point, and the precise ephemeris will give the precise XYZ. So if we want to give obtain the precise information, so we will replace that XYZ with the our navigation file. So with the help of these two files and this sp3 format and RINEX, we can have the precise location of any point using the GPS files. Okay, thank you.